All right, so let's look at the product rule in this video. We're going to derive it, not really formally, just kind of using some geometry and a little intuition, and then we'll do an example with it. So here's the way it works. We're going to start with just a rectangle here, height h, length l, and the rectangle has expanded where L is now, the length is really L plus this little extra change in L, and the height has something similar done with it. And so we want to compare the original area to the new area, and we want to find an expression for how much the area changed by in terms of these four things. So the original area is just this part right here. So that part is really just h times L, right? Or L times h. So I'm going to put here original area. Let me use a smaller pen. Okay, so the original area is going to be L times h. And I'm going to call that A. The new area is all of it. So that's the same thing as A plus whatever I've added to A, the change in it. And so that's really going to be L times H plus this region here, which is H times delta L, plus this region here, which is L times delta H, plus this little guy right there, plus delta L delta H. Okay, so then if I wanted to write just what delta A is, so that's just these three parts that are shaded, not this region, right? So that's going to be everything but the LH. So it's H delta L plus L delta H plus delta L delta H. So that's what we have. Okay, so let's scroll down. And now it says, now think of the rectangle as expanding, but this time only a very small amount in terms of the length and the width and the height. So instead of using the big deltas for the big changes in, we're actually going to switch them to little d's, right? These guys instead for small changes. And remember, we use the little d for really small changes, like essentially infinitely small changes. So if I do this, dA, little dA, and I rewrite everything, but I use little d's instead, then this line is going to turn into this line here. So h times small change in L plus L times a really small change in the height plus a really small change in L times a really small change in H. And remember, these are super tiny changes, so it's kind of like making this extremely thin here and here. And in fact, the idea is that you're essentially going to take a limit of that as that becomes infinitely small. Now, if it becomes infinitely small, let me move this out of the way, then these two terms are already extremely small. If I take two really small terms and I multiply them together, it gets even smaller. It's like multiplying 0.00001 by itself. That gets extremely tiny, so tiny that this guy essentially turns into zero. So we can pretty much ignore it. And I know that's sort of fudging this a little bit, but kind of bear with me here. That's going to say dA is basically the same thing as HDL plus LDH. Okay, and that's the key to this, really. Now, if the rectangle is expanding over time, then that means that the change in area is happening over a change in time. So if I said I want an instant change in area over an instant change in time, that's the same thing as this. Taking the change in the area over a very small change in time. And that tells me essentially how fast the area is changing with respect to time. So really that's just taking this and dividing it by dt. So I'm going to take this and divide it by dt. And so I'm going to get this. H dl over dt plus L dH over dt And really what that turns into, I'm going to rewrite it this way. H dl dt plus L dh dt. Okay, now this is the same thing as saying this. This now says area depends on time. Just like length depends on time and height depends on time. And if you think about it, if the thing's expanding over time, then I should be able to give you a time and you should be able to give me the length and height. So that means that h is really a function of time, L is really a function of time, and A is really a function of time. And so what happens here is if I have this, which I know is true, area always equals the length times the height, then I can actually write A prime, which is this, right? That's the same thing as A prime t. So now I know A prime t is equal to regular h, which is a function of t, times the derivative of L with respect to t, so that's L prime t, plus regular L, plus the derivative of h in terms of t. So this right here is what's called the product rule, and typically you see it written a little differently in textbooks. So in textbooks, you see this. F equals u times v, just like area equals height times length, where u and v are differentiable functions of x. Okay, so that means this basically says, so u and v are really functions of x, so it's like u of x and v of x, just like L and h were really L of t and h of t. So then this says, oh, and it says they're differentiable functions of x. So if they're differentiable, that means that these guys, u prime and v prime of x, exist. So that's what this part says right here, right? And f is the same thing as u of x times v of x, the regular u and the regular v, just like a was h times L. So what this says is f prime x equals the derivative in terms of x of u times v. So it's taking the derivative of the whole product here. And so that ends up being, if we just kind of treat it like this notation here, it's the same thing as u times dv dx in this case, plus v du dx. And a lot of textbooks, you'll also see it written this way. This is the same thing as u v prime plus v u prime. And sometimes you even see it written with all the x's there, because really these are all functions of x, so it's like u of x, v prime of x, plus v of x, u prime x, like that. So all three of these say exactly the same thing, and they're all called the product rule. So, you know, you can stare at that all you want, but I think it's a lot easier to see it in action in an example. So here it says differentiate two different ways. Multiply it out and then use the regular shortcut rule that we've been using, the power rule, or apply the product rule. So let's first do it the old-fashioned way. So first I'm going to distribute everything. I'm going to multiply it all out, so I'm going to get 2x to the fourth minus 4x plus x cubed minus 2. And so then if I take f prime of x using the power rule, I'm going to get 8x cubed, because this part turns into 4x cubed, and then times 2. Slope of negative 4x is really just negative 4. X cubed turns into 3x squared when I take the derivative, and the slope of a constant number is always 0. So if I rearrange this so that the powers are in order, 8x cubed plus 3x squared minus 4. There we go. So there's the old way, right? This is using the power rule and foiling, right? So now I want to try it using the product rule, where you don't actually multiply this out. So I'm going to start out writing the original again, 2x plus 1 times x cubed minus 2. And I'm going to call this one u and this one v. So I know that f prime of x is u prime, or let's do it the way that it's written up here. It's uv prime plus vu prime, like that. Okay. Well, u is 2x plus 1. V prime is 3x squared. V is x cubed minus 2. And u prime is 2. And so if I multiply all this out, I get 6x cubed plus 3x squared plus 2x cubed minus 4. And then if I simplify that, I get 8x cubed plus 3x squared minus 4. There we go. So you can see same thing either way. Now in the first example, in this example, it's probably easier to just do the power rule. Like multiply it out, use the power rule. But you can imagine if this were like 7 or 8 terms long, v were 7 or 8 terms long, or u were 7 or 8 terms long, it would be a lot more painful doing it that way. So product rule would be easier then. Oh, one other thing, we have to find f prime 2. So to find f prime 2, well, we already have f prime. Either way, it's one of these two guys. So f prime of 2, we just plug in 2 into the derivative. So it's 8 times 2 cubed plus 3 times 2 squared minus 4. So let's see, that's 64 plus, what is that, 12 minus 4, so 72, I think is what I'm getting. Okay. We'll do this next example too, just to get that one done. So y equals uv is the product of u and v. Find y prime 1 if all this other stuff. Okay, so y equals u times v. So if I do y prime, well, that's really going to be u prime v plus v prime u, or let's do it the way that it's written above, uv prime plus vu prime. And so u, but the problem is we don't know what any of these things are. We don't know what u or v are. But I need y prime at -1. Well, that's going to be u of -1 times v prime of -1 plus v of -1 times u prime of -1. And I do know what all of those are. And so those are going to be, let's see, u of -1 is 2. So this guy's 2. I'm going to multiply by v prime of 1, which is -3, plus v of 1, which is, v of -1, which is 3, and then times u prime of -1, which is 5. So this is going to be -6 times 15, which is not times, sorry, plus, which is 9. So there you go, a couple examples. We'll do more in class. Hope that helped.